Hi, my name is Michael Karagounis. I'm teaching electronics at the Fachhochschule Dortmund, or University of Applied Sciences and Arts, as our school is officially named in English. I'm head of the Integrated Circuit Design Laboratory, which deals with research in the field of analog, digital and mixed signal CMOS circuits. Today I will talk about our RISC-V activities and about our project, which aims at the development of a radiation-hard microcontroller for high-energy physics experiments. I will first introduce you to our application and also to the very challenging environment we are facing, especially in terms of radiation. Afterwards, I will present our project status. So the project is not yet completed, but I will show you how far we have come so far. And finally, I will show you what we are still planning to do. So FH Dortmund is member of the Atlas and the RD53 collaboration and is involved in the development of microchips for the experiments installed at the LHC, which is located in Geneva, Switzerland. At the Large Hadron Collider, protons are accelerated to very high energies, up to several tera-electron volts, and are brought to collision to study the resulting elementary particles. For example, physicists are interested in the particles' trajectory, but also their mass and charge. And for that purpose, 4 huge machines have been installed 100 meters underground, and one of them is the ATLAS experiment shown here in the right. And you may notice the people standing next to the experiment to emphasize the stunning dimension this machine really has. Our group is involved with the innermost part of the experiment, which is the pixel detector, which is mainly used for particle tracking. As is shown here down on the left, the pixel detector consists of several layers shaped like barrels, which are placed around the beam pipe. And in turn, each layer consists of several modules, which are shown here in the right. And the module is built of a sensor element and several readout chips bump bonded to the sensor. With the upcoming high luminosity upgrade, a new powering scheme is introduced to increase the powering efficiency of the pixel detector. As you can see here in this diagram, the detector modules are now placed in series instead of in parallel, and they are supplied by a constant supply current instead of a constant supply voltage. This modification also raises the need for a new detector control system adapted to the requirements of this new powering scheme. In this new detector control system, it was initially planned that the DCS chip is able to switch off each pixel modules individually by bypassing its supply current. And in addition, it has the task to monitor the supply voltage, so the voltage drop across a pixel module and its temperature. Several of these DCS chips are controlled by the DCS controller chip, which acts like a communication gateway. So these chips interact with the DCS controller in a master-slave communication approach, and in turn the DCS controller communicates over a CAN network with the computers in the control room and gets its command from there. Now in our group, we are mainly concerned about this DCS controller chip. The responsibility for the design of this chip has been assigned to us. The DCS controller chip is a mixed signal design, as you can see in this block diagram. It has a CAN unit, it has also the unit for the master-slave bus, but it also has the full required infrastructure like voltage regulator, a power and reset circuit, an oscillator, and an ADC for some sensoring application. Now there is the need to establish a communication bridge between the CAN network and the master-slave bus. And this bridge has also to take into account that CERN, or at least the ATLAS experiment, follows the CAN-open standard. So CAN-open defines a special memory structure called the object dictionary, and communication data is organized in objects, so in service data and process data objects. So the bridging logic has to take into account this CAN-open approach. Usually in a commercial or industrial application, this functionality would be established in software, would be implemented in software. However, in our community, due to the harsh radiation environment, we don't use programmable systems at the moment. So the standard approach in our community is to use hardwired logic, and this is also what we have done for this project. We have written a Verilog model to implement this bridging logic, and the chip is back in our lab, and we are characterizing it and also irradiating it at the moment. However, hardwired logic is not very flexible, and if there is the need for some modification, the only way to implement this modification is to resubmit the chip, right? So it's not very flexible. If the requirements have changed, or if a severe bug has been found, the only way to take this into account is to resubmit the chip. So that's the reason why we started thinking about microcontroller cores as a method to increase the flexibility of our systems by means of firmware updates instead of costly and time-consuming resubmissions. And we think that the RISC-V architecture, due to its open approach, is a natural candidate for such kind of applications in the scientific community. So perhaps you're now wondering why programmable systems are currently not used in high-energy physics experiments, at least not in the active zone inside the experiment. And I think a better understanding of how radiation affects electronics will help to clarify this. So the electronics in the experiment are located in a complex radiation field, which of course includes protons, but also neutrons and electrons, which are generated by the interaction of the protons with the materials used in the experiment. For the same reason, also electromagnetic radiation is generated, like high energy photons and gammas. And this radiation field influences this electronics now in several ways. First, we have total ionizing dose effects, TID effects, which increase in intensity as a function of the absorbed dose. A prominent example is the shift of the transistor threshold voltage. Then there are collisions with particles, which can lead to a displacement damage in the semiconductor crystal, and which can lead to increase of leakage currents, for example. And in addition, there are effects which have only a temporary influence on the electronics, like radiation-induced bit flips in the logic and the memory, so-called single event effects, which lead to data inconsistency and corruption. These effects are temporary because if you reset your system, these kind of defects disappear, while TID and displacement damages effects remain. So the electronics installed at the inner layer of the pixel detector X is expected to absorb a dose of 500 megarad over lifetime. And we hope that the chips we are developing at the moment will also sustain 1 gigarad. But the minimum they should bear is 500 megarad. Now this number for non-experts is very abstract, so to get a better understanding, you can compare these numbers with those which electronics in space applications are absorbing, usually like in a satellite. There we have in a near orbit mission like 100 kilorad, which is several orders of magnitude smaller than what we are expecting in the LHC after the high luminosity upgrade. So it's a much more severe and challenging environment than with space electronics. The SEE rate, so the rate of single event effects, is estimated to be around 60 Hertz, which is quite a lot. And one advantage in comparison to space application is that we are not expecting heavy ions. So heavy ions in space application, when they interact with a semiconductor crystal, a lot of charge is ionized, and this charge flutes the chip and can lead to latch up and can create a lot of data inconsistency. So these kind of heavy ions we are not expecting, and this is an advantage in comparison with space application. Now let's dwell a little bit more in TID effects. The susceptible structure of the MOS transistor is not the metal or the silicon, but the oxides. penetrating particles can ionize electron hole pairs in the oxides. And while the electrons can easily leave the oxide through tunneling effect, the holes cannot because they are trapped in defects which are produced in the oxide during production. This affects the transistor threshold voltage, which with NMOS has the effect that the threshold decreases, while with PMOS the threshold increases. In addition, due to the interaction with the radiation, hydrogen is released in the oxide, and these hydrogen ions slowly travel towards the oxide silicon interface, and there the hydrogen ions form interface charges which are positive for the PMOS while they are negative for the NMOS. So in both cases the transistor threshold voltage is increased due to these interface charges. To make things even more complicated, the traps and the interface charges have different time constant. The traps charge up faster than the interface, meaning that the traps are filled at smaller total ionized dose, while the interfaces need a higher dose to get filled up. In addition, TID effects are bias and temperature dependent, so hot environment leads to more radiation damage than a cool environment. And also a biased transistor sees stronger radiation effect than an unbiased transistor. We are designing this chip in a 65 nanometer CMOS technology because studies have shown that technologies with thin gate oxides are less sensitive to radiation than older CMOS technologies with thicker gate oxides. The technology we use has a gate oxide thickness of 2 nanometers. However, measurements show that transistors in this technology are influenced by radiation stronger than we would expect based on the gate oxide thickness alone. So this plot shows the variation of the on-transistor current for minimum sized PMOS and NMOS transistors as a function of the absorbed dose. As you can see, the NMOS on-transistor current first rises because the traps in the gate oxide are first filled up by ionized holes. But for higher doses, both the NMOS and the PMOS current is reduced significantly. So especially the PMOS transistor current is reduced by 100%. And the reason for this is that apart from the gate oxide, there are other oxide structure with much larger thickness in the transistor. For example, the shallow trench isolation, which is used to isolate different transistors, and the oxides used in the spacers. These oxides reach thicknesses of up to 100 nanometer. However, this plot looks worse than it is in reality because this measurement has been performed at room temperature, while the chips in the experiment are operated at minus 30 degrees Celsius. So we expect a degradation of 30% in the digital part, which we take into account as additional process corners during digital implementation. So we characterize our standard cells with special radiation models for specific TID. In addition, transistors in the analog part with longer and wider channels are influenced even less than that. While we think that we can deal with TID effects, we expect SEE effects at the estimated rates to be more challenging, especially within the memories of the microcontroller system. One category of SEE is SEUs, single event upset, which leads to bit flips in storage elements like latches, flip-flops, or in SRAM. Now let's assume that the shown latch stores a logical 0. Then we have two reverse biased PN junctions in the circuit, which would collect any charged ionized by penetrating particles and therefore are especially susceptible to radiation. Now if you focus to the PMOS transistor, we will see that the collected charge is not purged immediately to ground through the NMOS transistor due to its non-zero on resistance, but builds up at the gates of the transistors M2 and M4, and in turn flips the stored bit from 0 to 1. As a result, the stored data is corrupted. The same or a similar effect can also influence the output signal of logic gates, But since there's no storage element involved, the output signal of the logic gate goes back to the nominal level after some while, and therefore the respective effect is called single event transient. A common approach to mitigate single event effects is triple mode redundancy. Digital circuits usually consist of several stages, all having combinatorial clouds and storage elements like flip-flops. To protect against single event upsets, the flip-flops are triplicated. The output signals are majority voted and fed back to the flip-flop inputs via multiplexers. To protect against single event transients, also both the majority voter and the combinatorial cloud are triplicated. By this means, a voter or a cloud which is hit by a particle falsifies only the data of a single flip-flop and not all three of them. Of course, triple mode redundancy has a strong penalty on area, speed and power, and one key aspect of this project is to quantify this impact exactly. Now in the remaining minutes I would like to present you our project status. Let's start with the core. We have chosen the RISC-V core from Fraunhofer IMS Institute here in Duisburg. This core is based on the former V-Scale project from Berkeley University. It deploys a 3-stage execution pipeline and a AHB light bus interface. The only modification we have applied to this core is the addition of an optional hardware accelerator for artificial intelligence and machine learning applications. Since we are new in the microcontroller and firmware development business, the first item we addressed was setting up the environment to generate programs for use in simulation and FPGA prototyping. So we managed to get the Eclipse GNU MCU flow running for software developing and debugging in combination with our FPGA prototype. And for simulation we use the data-to-mem Xilinx tool in combination with self-written software to generate mem files. At the moment we also use the Sci5 software development flow because of its tight integration with the RISC-OVP virtual prototype simulator. But in future we are planning to integrate the RISC-OVP toolset with the GNU MCU flow. So as the next step we started ASIC implementation based on the Cadence design flow we have available in our lab. So we use Xcelium for simulation, Genus for synthesis, Innovus for place and route, Calibre for DRC. Okay, this is a mentor tool, but still we used it. QRC for parasitic extraction and Voltus for sign-off power simulation. At the right you can see a first layout we were able to produce without pad. It has an area of 3.36 millimeters times 2.32 millimeters. The largest part of this area is consumed by two big SRAM blocks of 2 megabytes each. One SRAM block is used for the core as data and instruction memory, while the other is used for the machine learning hardware accelerator. In addition, the area in the center assigned to the core is not fully used at the moment. As you can see, the largest part of the area consists of filler cells, so this blue part are mainly fillers. The reasoning behind this choice is that we expect the design to increase when we apply triple mode redundancy or other methods of protection, and we want to avoid resizing the floor plan to avoid distortion of the power simulation results due to larger signal wires of an enlarged floor plan. We managed to run a first sign-off power simulation, including layout parasitics. We run the core at a supply voltage of 1.2 volt and a clock frequency of 25 megahertz, and we execute a specific test program. And during the execution we consume 4.589 milliwatt of power. However, what is very interesting is that 60% of this power consumption happens in the SRAM blocks. So it seems that SRAM access is very costly in terms of power, which is noteworthy because you will need continuous SRAM operations to protect the stored data against SU. So we will read out the data, run some hard channel encoding or decoding to correct for errors and writing the data back. So this will cause a lot of power consumption. So to summarize, We are able to develop software for the core, and we can program and debug the core when it is prototyped on an FPGA board. We are able to execute digital implementation and to run sun-off power simulation. So what comes next? Next is the application of triple mode redundancy on the full design, and to study the influence of the triple mode redundancy approach on power, area, and timing of the core. In addition, we have to develop a method to protect the SRAM data. For example, we could store the data Hamming coded and cyclically read out the data, perform an error correction, and write it back. So there would be the need for a specific memory controller which performs this task whenever there's no memory access from the core, or in parallel to the core access by using a dual port memory, for example. In addition, we would like to elaborate by single event upset and single event transient simulation if triple mode redundancy is required in all core parts, or if there are some parts which don't need to be protected in that way. We want to study alternative protection methods. So we want to study channel coding theory and see if there's any other method which leads to better results in terms of power, area, and timing. And by this means we want to find an optimum in the trade-off between protection against SEU and area, power consumption, and speed. And finally, of course, at some point, maybe at the end of the year, beginning next year, we will produce a prototype. And when this prototype comes back from production, we will perform irradiation studies to see if the applied strategy is working out and if we have a safe microcontroller, immune and robust against SEU and irradiation. So thanks a lot for your attention, and thanks a lot for the opportunity to talk about this very exciting project.